Like I said, today we are going to start the last new material before our mid-chapter test. We want to be making sure that we're getting all those homeworks turned in so we can have opportunities to open note tests, right? And trying to stay off our technology because, again, open note tests are a gift, right? Right. So we're only going to do half of the material today. We're going to be solving radical equations. This is obviously equations that have radicals in them. Now, we have dealt with more than one kind of radical so far this chapter, haven't we? We've done square roots, cube roots, fourth roots, fifth roots. In my equation solving, I'm going to stick with square roots and cube roots because these are the most common. Today, we're just going to work on the square roots. We'll do the cube roots tomorrow. So that means tonight, you should start the homework and you will have the ability to do all of these square root questions in the homework. And I'm pretty sure that I separated them pretty well, like the left half is the square roots and the right half is the cube roots or something like that. But the point is that they're not mixed up. Alrighty, let's jump right into it. When you're solving for x, remember what you're trying to actually do is you're trying to undo the order of operations. So when solving for a variable, your job is to peel the onion, get to the variable by following SADMEP. That's PEMDAS in reverse order. So we'll start with addition and subtractions if they exist, and then we'll handle the divisions and the multiplications if they exist, and then we'll handle exponents. And remember, radicals are exponents. And of course the P stands for parentheses. If there's crap inside the parentheses, we would deal with it last. Okie dokie smoky, here we go. Looking right here, following SADMEP, trying to get this x by itself, which thing would I need to cancel first? Well, there is no addition and subtraction that is outside of the radical. And since the radical is actually an exponent, we can't handle that first. So since there is no addition or subtraction on the outside of this radical, the first thing we can do is cancel the division or multiplication. This 2 that sits in front of this radical is a multiplication. And we can cancel that with the division. So we will go ahead and divide both sides by 2. That leaves me with the square root of x plus 1 equals 2. We're trying to peel the onion. How do I cancel a square root? What is the inverse operation of square root? Square. And the reason why square is the inverse operation is because it is the reciprocal exponent. Recall from the last few sets of notes, this is actually the 1/2 power. So if we raise it to its reciprocal power, the 1/2 power and the second power will cancel each other. Here's me squaring both sides. So we get to do this like that. Now this does not create a plus or minus. Canceling a square creates a plus or minus. We didn't cancel a square. We canceled a square root. Remember, you cannot take the square root of a negative number, which is why we don't need to say plus or minus, because the minus would have been impossible. What we're left here is x plus 1 equals 4. Subtract 1, and you will be finished. You get x equals 3. I do need you to be very careful, though, with square root equations. Sometimes the algebra can generate an answer that is not allowed. If you remember from previous chapters, we call that an extraneous solution. So all I need you to do is to check to make sure you are actually allowed to substitute this answer in. What do I mean by that? What I mean is if you were to plug it in, it wouldn't have you taking the square root of a negative number anywhere, because sometimes that happens. You see, we canceled a square root. The square root is what has the restrictions. So the moment you cancel it, the algebra technically could give you an answer that would have originally broken those restrictions. So we just take our answer and we make sure that we're allowed to plug it in. 3 plus 1, is that negative? No. So we're not worried about taking a square root of a negative there, so we're fine. That's it. It's that easy. You just check to make sure that plugging your answer in would not have made the inside of a square root bar negative, because we don't want to deal with imaginary solutions. We cool? You good with that idea? All right. And, you know, it's not something I do all the time, but I was thinking, wouldn't it be neat to see this on Desmos, to see what's actually happening? Because technically, that is one of the standards for algebra. It says that when you are solving equations, the student is supposed to understand that what you are solving for is the place where the two graphs would have crossed each other. And that is two different graphs. One of them was 2 square root of x plus 1. That was one graph. That's what a square root graph looks like. How about that? We'll get to that after the mid-chapter test. And the other one is y equals 4. And if you check, they cross each other at x equals 3, which is exactly what we found. Neat, huh? That's what you were doing. And so let me make this a better image for, there we go. Now everybody in the room should be able to see it a little bit better. That's what we just found. Pretty cool. Well, that did absolutely nothing. What did I click on? Oh, I clicked on the wrong program. That would be why. Well, we'll just wait for that to open on my end, and I'll close it. It won't affect you guys. Scooch. I'm only going to be doing the left side of the notes because the left side is where these square roots are. I'm going to be solving for the square roots today. We'll handle the cube roots tomorrow, and on Friday's practice, we'll do both. There. Now that I closed Active Inspire, I could try to get back to solving for x. So we're looking here. All right. Well, we're trying to get x by itself. The problem that we're going to have here is that x exists under two different radicals. And if those radicals didn't exist, well, it would be pretty easy, wouldn't it? So those radicals need to be our first target. We need to figure out how we're going to get rid of them. How do you usually get rid of a radical, a square root? How do you normally get rid of a square root? Square it. The problem is, you can't just say square both sides. You can't. You can't just square this side. That won't make those two square root bars go away. How come? Because there's a minus sign right there. Now, if this was a multiplication dot, yeah, I could just square that side and, well, both sides, and the radicals will be gone. But it won't work the way it's sitting. So how can I make it so that squaring both sides does get rid of the square root bar? Well, if I put them both in parentheses, I would still have this thing, though. This thing is what's causing me the problem. But if I did that, here, let me grab a piece of scrap paper and show you what I'm talking about. And if you're okay with it, I'm going to use numbers and no x's. Is that cool? Let's just say for the sake of argument for a moment here that it says the square root of 25 minus the square root of 9. And the reason why I chose those is because we know what the square root of 25 is and we know what the square root of 9 is, right? What is the square root of 25? It's 5, and the square root of 9 is 3. So we know that this is actually equal to 2, right? But watch this. If you try to square this, here's what it doesn't equal. It does not equal 25 minus 9. Because we know for a fact that the square root of 25 minus the square root of 9 is 2, right? But 25 minus 9 does not equal 2. So we know this is not allowed. But why is that not allowed? What's happening? Why is that not working? Because when you put an exponent on a set of parentheses, remember what that means. It means that set of parentheses times itself. This 2 is implying that you were doing this. And you would have to FOIL. And we don't want to do that with this. We know that minus sign is the problem because we know squaring would get rid of the radicals. What do you think? Yeah, if we move one of the radicals to the other side, then we could square both sides and we would cancel both square root bars. Good. So let's go ahead and move the square root of x plus 7 to the right side. Which will leave us with the square root of 2x plus 5 equals the square root of x plus 7. The square root bars are still the problem, but since all that exists on the left is a square root thing, and all that exists on the right is a square root thing, we can cancel the square roots on both sides by squaring. Now it won't be an issue. So we will square both sides. Leaving me with an algebra 1 question, 2x plus 5 equals x plus 7. It's algebra 1 from there. Get the x's to one side, get the things without x's to the other. I don't like to have to deal with negative x's when if I can avoid it, so I'll go ahead and subtract an x from both sides. And then subtract a 5 from both sides, and this question is finished as long as the answer that we just found does not break the rules of a square root bar. It says x is 2. And we just have to make sure that plugging in a 2 does not give us the square root of a negative number. Plugging in a 2 here gets you the square root of 9. 2 times 2 is 4. So square root of 9, plugging in a 2 there, square root of 9, we're good to go. It works. What do you think? Easy ones, not too bad? So far, so good? People at home, any questions you'd like to ask me? Anything? Or is it still easy peasy lemon squeezy? Thumbs up if we're good at home, since everybody's muted. All right, got 2, 3 thumbs up. All right, that'll work. Cool. Then let's flip it over to the ones that are not so straightforward. That's not even a radical, is it? But that doesn't mean that you don't know how to do it. You can handle this. And the reason why is because of what I said in the very first example when I was describing how we were canceling a square root with a square and why it works. Remember, I was talking about when you cancel a square root, what you're actually doing is raising both sides to the reciprocal power. So you do know how to do that. All right, well, let's go ahead and tackle it. Still following SADMET, PEMDAS in reverse order. What would I do first here? Subtract 2 works. Minus 2. It's going to give me 2x raised to the 3/4 is 8. I've already said it twice, these notes now. When you want to cancel an exponent, like a square root bar, because that is an exponent, when you want to cancel an exponent, what you have to do is raise both sides to the reciprocal exponent. Yeah, what's up? You can make the exponent a radical if you'd like to. I don't want you to have to do that, but I'm gonna go ahead and do it that way real quick, just because it's good to see that it works. When I say I don't want you to have to do it that way, there's absolutely nothing wrong with it. I just feel that sometimes it's more work, but I am more than happy to go ahead and do it that way, and then I'll do it without the radical, just so you can see that in my opinion, it's a little bit faster. I don't know, maybe it's not. Who knows? You know what? You just did it because it was 2? Oh, because you could see that the 8 wasn't going to give you much trouble. So let me go ahead and record this like so. All right, so we'll handle it that way first. So no one needs to write this down unless you want to have it this way, but I'm going to do it I'm going to use the reciprocal exponent in my notes, but it won't be a problem. So this is a fourth root, yeah? And this is a third power. So Lewis, did you put the third power on the inside or outside?
Inside.
On the inside. Interesting. I would have done it the other way around, but it doesn't matter. So you say we have a fourth root like this. It absolutely will not matter, okay? It's just that, remember your next test is no calculator, okay? So if I do this, say I put this 2x in here and I leave the third power on it, the first thing I'm going to have to do is cancel this fourth root. How do I cancel fourth roots?
Well, what I did was I did 2 to the fourth power, or 2 to the third power,
Yeah.
8, and then fourth power is 8 too.
You mean you fourth rooted 8?
Oh, I guess so.
All right, so here's how I would have done this. And I would have started peeling that onion. I mean, that's essentially what I'm going to do. I'm just going to do it in a different order, okay? But yes, you can absolutely use these radicals if you'd like to like this, but you don't need to. So then I'm going to stop it right there and go to this method instead, which I'm going to end up with those radicals anyway, just in a different place. What I'd like you to do, because I'd really like to drive home the concept that the radicals are exponents, is I would like you to raise both sides to the reciprocal exponent. That's going to be the 4 over 3 power. When you raise a power to a power, you are multiplying your exponents. And when you multiply reciprocal fractions, they cancel one another out. What we have now is a 2x equals 8 to the 4 thirds. And we tackled things like that in the last 2 days in our notes and in our practice. We can evaluate 8 to the 4 thirds by hand. I don't know what 8 to the 4th power is. So I'm not going to make it a big number and then try to make it small. I'm going to make it a small number and then make that big in that order. I'm going to say that this is the third root of 8. There's my over 3. And I will then raise that to the 4th power. So this is the 4 over 3 power that you see right here. Now, Lewis, what we had just talked about right here, notice the radical that I have in black and exponent, the radical and exponent that I have in blue. On this side, it's 4th root 3rd power, but on this side, it's 3rd root 4th power because of reciprocals. So like, you can't see what I'm pointing at. So like I was saying is, it was going to happen eventually. I just didn't want you to have to do them twice because now I'd have to take the 3rd root of both sides and then have to raise it to the 4th power. This cuts a step out. Absolutely not wrong, but this cuts a step out. What is the cube root or 3rd root of 8? It's 2. I'm glad Lewis is here because no one else has talked to me. So I have 2 to the 4th on the right side. What is 2 to the 4th power, though? 16. Like I said, I'm glad Lewis is here since no one else is talking. Then you just divide both sides by 2. And you get x equals 8. Well, you really don't have to be concerned here because, this was 2 times 8. So there was no way you were ever going to get a negative anywhere. So don't even worry about it. Really, if you were worried about it, you would have thought about it being set up like this. You cannot take the 4th root of a negative number, but since I got a positive answer, you were straight. Wasn't anything to even worry about. Yeah, what's up?
So you need to put the reciprocal on both sides.
The reciprocal power, yes. And we did that on the front. It just didn't look like it. Remember that this square root bar, this is the 1/2 power. This 2 is the 2 over 1 power. So we did raise both sides to the reciprocal exponent. The 2 over 1 is the reciprocal of this 1 over 2. It was happening, it just didn't look like it. And I forgot to graph my last two examples, but I do think it's worth seeing. So I'll go ahead and graph this one that we just did. We have 2x raised to the 3/4. I'm going to do 3/4 as 0.75. The 3 over 4 power is 0.75. And then plus 2. And we set that equal to x or y equals 10. And I need to zoom out. There you go. Look at that. X equals 8, just like we found. Ta-da! Neat, huh? So cool. I can't wait to do the last one on Desmos. Last one for the day on the left. Remember, what does the 1/2 power mean? What is that actually? Come on, you guys know. What's the 1/2 power? Lots of people should be able to tell me. It's the square root. 1/2 power is the square root. So I am going to set this up with a square root symbol. Why did I do that though? Because, remember, I wanted you to be able to check to see if your answer or answers were going to give you a negative underneath a square root bar. The way it's sitting, it doesn't look like a square root bar. You could just raise both sides to the reciprocal power right here. But I want you to see the square root bar. Okay? That's what you did? Okay, well, we can do the reciprocal now. Okay? And as long as you know that the 1/2 power means square root, and you can keep that in your mind, then you're set. It's just that I find that students forget that that means square root, so they forget to check their answers. And it's the only reason why I ask you to write it like this first. But we are going to need to raise both sides to reciprocal power, which Tex you obviously know is a 2, because you said you did it right away. So we'll go ahead and raise both sides to the 2 over 1 and cancel this. It leaves me x plus 6 equals x squared. This has x's and x squareds. Do we remember how to solve things that have x's and x squareds? Does that mean that nobody remembers? Or that you just don't feel like talking to me? Ah, yes, Nick. Do we remember how we would solve a setup like this? When we have x's and x squareds, what we have to do?
I would think that you, well, initially I would think you have to like subtract the 6 and then like square root everything.
But, well, if you square root both sides, you're just going to get back to where you were. That wouldn't benefit us at all, would it?
My question was,
Yeah?
how did that 1/2 turn into a 2?
No, the 1/2 didn't turn into a 2. This 1/2 is the blue square root.
Oh,
The 1/2 power is the square root.
alright, so
Because if you remember, the index, even though we never write it, the index, or that won't be able to see that color, of a square root bar is a 2. So it is they want to think of it as like the 2 root. So this says the 2 root, the square root. We canceled it with its reciprocal power, which is 2 over 1. So the first thing I did was rewrite the question with a square root bar in it, instead of a 1/2 power. Okay. Ohm, what do you got for me, dude?
I think you divide by x.
Now, I'd love to divide by x, but it is a big algebra no-no to divide by the thing you're trying to solve for. Not to mention, if we divide by x, you actually have to divide all three things by x. That means you created a fraction of 6 over x, and oh my gosh, that just is even worse. Come on, guys, what do we got? I mean, it's good to think that way, but because it gives me an opportunity to tell you guys why we can't do it. In mathematics, you never ever divide by the thing you're trying to solve for. You eliminate solutions when you do that. Hmm? Well, if I multiply by x, I have an x squared, a 6x, and an x to the third. Hmm. Hmm. The way we solve polynomial equations is to get it all to one side and factor it. When you have things, when you have x's with exponents and x's without exponents, the only way to solve this is to get all your x's to one side. And actually, you need to get the 6 to that side as well because it needs to be equal to 0 in order for factoring to work. Yes, Nick?
So when you subtract x squared, you get negative x squared plus x plus 6.
I could subtract x squared, but I don't like factoring when my front thing is negative. So what I'm going to do is I'm going to subtract both of these objects and bring them over. That way the x squared stays positive. It would get you to the same result, but factoring with a negative on the front is harder to do. So I'm going to go ahead and subtract this x and this 6 from both sides. And it will give me that 0 equals x squared minus x minus 6, which factors very quickly because there's no number in front of the x squared. That makes life good. We just need to figure out which two numbers multiply to negative 6 and add to negative 1. What two numbers multiply to negative 6 and add to negative 1? Negative 3 and positive 2. Negative 3 times 2 is negative 6. Negative 3 plus 2 is negative 1. Negative 3, positive 2. The order of these parentheses does not matter. We now see that we have two solutions. Remember, we get our solutions by figuring out what makes the insides equal 0, right? So my two solutions are x equals 3, because 3 minus 3 is 0, and x equals negative 2, because negative 2 plus 2 equals 0. We have two solutions. We need to check them, just to make sure we weren't trying to take the square root of a negative number anywhere. We start with this 3. I'm going to go right here because that's where my square root is. 3 plus 6, that says the square root of 6 is going to be the square root of 9 is 3. And if you plug it in right there, oh yeah, so 3 equals 3. That's pretty good, right? That works. Let's plug in negative 2. Luckily, negative 2 plus 6 is not a negative number. But I can plug this x into more than one place. So let's check. Plug in the negative 2. We get the square root of negative 2 plus 6. That's 4, right? The square root of 4. What's the square root of 4? 2. So we plug in this negative 2, and we get 2 equals negative 2. Uh-oh. 2 does not equal negative 2. See, when you plug the x in, you actually have to go to more than one place if there's more than one x to plug it into. Here, there was only one x to plug it into. I don't know if you guys caught it, but here, I plugged the 2 into both x's. So I just had to make sure that I didn't make the inside of a radical negative. And here there was only one x to plug it into. I just had to make sure I didn't make the inside of a radical negative. But this time, the difference was I had x's in a radical and x's out of a radical. Make sure you always check the answers to see that they work. When you plug in 3, you get the square root of 9 equals 3 because there's a 3 right there. And that works perfect. You plug in a negative 2 and you get the square root of 4 equals negative 2. Square root of 4 does not equal negative 2. So this is an extraneous solution that the algebra gave us, but it does not work. The only real answer is x equals 3. No. The red 2's don't actually exist in the beginning of the question. Remember, the beginning of the question says the square root of x plus 6 equals x. That's the beginning. So if you plug in negative 2, you get the square root of 4 equals negative 2. And it really, really doesn't, right? The square root of 4 is 2. So why did this happen? What created the extraneous solution is the question. What created it was what Lewis just said. The squaring is what created the bad answer, because the squaring got rid of the square root bar, and the square root bar was the part that had the restrictions. When you eliminate restrictions, Sometimes you create bad answers. So that's why you have to check. Is it possible that a setup like this would have had two answers? Absolutely. Is it possible that they only have one solution? Well, of course, you just saw it happen. Is it possible to get zero solutions? Absolutely. You always have to check. So just so you can see what's going on graphically, that way you know why there's only one solution. Let me go back to my home. There we go. And do x plus 6 raised to the 1/2. X plus 6 raised to the 1/2, which is, I'm just going to say 0.5, which is the same thing as saying the square root of x plus 6. And I'm going to set that equal to y equals x. Here is your one solution at x equals 3. Where did the extraneous solution come from? The extraneous solution came from here. You ready for this? And oh, hold on, don't worry about it. What I'm going to do is I'm going to square both sides. Okay, so here's the original setup. We see graphically that, yeah, there is only one answer. There will never be another answer. You see it. It's happening right there. But the moment we square the left, so that was me raising the left side to a 2 and me raising the right side to a 2, this is what the graphs become. And what you did was you created this answer that does not exist. So if I graph the originals, I want you to notice that this point and that point are vertical from one another. Basically, the extraneous solution graphically was trying to tell you that if this parabola continued this way, because this is half a parabola, it's saying if it continued this way, you would have had this answer. That's what it was trying to tell you. It was trying to say that if the other side existed, meaning if you did square it, this answer would have existed. But we don't have the other side. And that's why there's only one real solution. I think that's neat because I'm a huge nerd.